Hello guys, welcome to my YouTube channel or David Structure Hub. So this is a place where you learn, build and innovate. So if you are not part of this family, I kindly request you to subscribe to this channel to be part of this family so that you may know more or learn more about structures. So today I want to talk about a three-moment theorem or the theorem of three moments. And I want to tackle a question from a past paper. This is Kenya National Examination Council, question number 5, October-November 2016. So this is the question, and it reads, Figure 4 shows a loaded continuous beam using three-moment theorem. Part A, analyze the beam and hence plot bending moment diagram indicating values at critical points. Part B, calculate the reaction and hence draw shear force indicating the critical values. So before I begin, I just want to mention one thing, and that is outside what we are going to do today. So I know some of you have been on site, that is construction site, and there is this notion that people talk about during the construction of a project, maybe a structure like a building, etc. So you have heard people saying that it is better to go for uh, over reinforced concrete and not under reinforced concrete. So they have so many reasons as to why they choose over reinforced concrete rather than under reinforced concrete. So what is your view about over reinforced concrete and under reinforced concrete? So in my next video, I will be talking briefly about under reinforced concrete and over reinforced concrete and their effect on structures. And also I will be also talking about an economic design, our question of today. So this is our question. This is a beam. It is a continuous beam, meaning it has more than two supports. So support A, support B, and support C. And then it is loaded with both IUDL and a point load. So as you can see, it has IUDL of 16 kilonewton and then IUDL of 22 kilonewton per meter. Again, it has varying I or EI. As you can see, at span AB, there is I, and BC, there is 2I. So we will automatically apply the second equation of Clapeyron theorem of three moments. So solution. The first thing to do when you are given such an equation is to create a space to draw shear force and bending moment diagram. So extend this line to give you enough space to draw the diagram required. So like that. So after doing so, now you start calculating the moment for such a beam. So solution. The first thing to do is to calculate the maximum bending moment for free spans. So you start by calculating free span moment. Free span moments. So we have two span AB and span BC. So let's begin by span AB. Span AB. As you can see, span AB is loaded with uh, a point load, and it is eccentrically placed on the beam. So meaning the formula for maximum moment, so M max is equal to WAB over L. So that is the formula uh, when a simply supported beam is eccentrically loaded. So this one will be 16 times 2 times 3 over L is 2 plus 3, that is 5. After doing so, you insert the figures in your calculator and you will get the answer. So that is 19.2 kilonewton meter. After doing so, you will proceed to span BC. So span BC is a simply supported beam, and it is loaded with a UDL, a uniform distributed load. So what is the formula for a uniformly distributed load beam? So it is WL squared over 8. So span BC equals to WL squared over 8 equals to 22 times L. L is 5, so it will be L squared, 5 squared over 8. So this one will give you 68.75. 68.75 kilonewton meter. After doing so, the next thing to do is to draw free span bending moment diagram. So let's draw a free span bending moment diagram. So let's do it here. That is a baseline like that. And then you approximate the values. We have 19.2. Let's approximate there. So this one will be a triangle. So from here, so the H is what is 19.2. And then we have span BC 68.75. So it will be a little bit higher than 19.25. So the UDL will bend in a parabolic shape. So a UDL bend in a form of a curve, and that shape is a parabola. So the height is 68.75. After doing so, the next thing to do is to apply the Clapeyron three-moment theorem. So as you can see, this one is a loaded beam with a varying EI or I. So the formula to apply here will be, now apply three-moment theorem. How do you apply? So we know that at A, here at A, we will have moment A. Here at C, we have moment C. Here at B, we have moment B. So to apply three-moment theorem, we will consider two consecutive spans. So two consecutive spans. Let's begin from A going forward. So that is span AB, span BC. Something to note, for you to apply three-moment theorem, you will have to consider the two consecutive spans that follow each other. For example, span AB and span BC, and then you write the formula. So like here, we have ABBC. So we will have MA L1 over I1. Because MA is here, it is bordering span L1. So this is L1 and this is L2, like that. So plus 2 MB into bracket L1 over I1 plus L2 I2. You close the bracket, plus MC L1 I1 is equal to minus 6 A1 X bar 1 L1 I1 plus A2 X bar 2 L2 I2. So that is the formula for Clapeyron three-moment theorem, and when EI is not constant. So after doing so, let me create space for more calculation. So let me write the formula here. So we have MA L1 I1 plus 2 MB L1 I1 plus L2 I2 plus MC L2 I2 is equal to minus 6 A1 X bar 1 L1 I1 plus A2 X bar 2 L2 I2. So after doing so, the next thing to do is to calculate A1. Now calculate A1 X bar 1. So for this case, our area 1 is this one. So you will calculate the area for this one and then the x bar, which is the centroid for this triangle. So you can use two methods. So let's begin. So we know the area of a triangle is a half base times height. So this 0.5 times a half base times height. So the base is 2 plus 3. So that is 5 times 5. And then the h. H is the maximum bending moment. So which is 19.2. So times 19.2. Now this is the area. How about the x bar? So the x bar, we can use b plus 3, b plus l, b plus l over 3. That is the formula for x bar. And here, our a is this one, and our b is this one. So this one will be 0.5. Let's punch this one into a calculator and get the figure. So 0.5 times 5 times 19.2. So that is 48. So it will be 48 plus b is this distance plus 2 plus l. L is 2 plus 3. So that is 5 over 3. So this one will be 48. This is times, not plus. So 0.5 times 5 times 19.2. It will give you 48 times b is 2 plus l, 2 plus 3. That is 5. So this one will be 48 times 7 over 3. So our A1, A2 will be, let me punch my calculator, will be 112. So it will be 112. So don't bother about the SI unit. So let the figure remain like that. So our A1, x bar 1 is 112. So something very important to note, when calculating the centroid for this shape, which is a triangle, some of you may get problem because the centroid, you can calculate the centroid either from coming from this side going that way or from this side going this way. So the something to note about the how to determine where A and B is this joint. This is a common joint. This is a common joint. So remember, we selected our span A, B, B, C. B being a common joint. So a common joint, the length which is so close to common joint is our A, and the remaining one is B. So an alternative for this, you can also get the area of this smaller triangle times its centroid, and then plus the area of this another triangle times its centroid. So it will be the area for this smaller one, this one, will be 0.5 times 2 times 19.2 times the centroid for that one is 2 over 3 times 2. You put it in bracket plus the area of this one will be a half times 3 times 19.2 times the centroid for this one will be a third. A third times 3 plus 2. So this one will give you, this one is 25.6 plus you carry out the operation for this one. So here is 1, here is 1. So that is 86.4. So the final answer will be 112. So you can choose whichever method you feel is so safe to you or is the simplest for you. So again, when calculating the centroid for these smaller triangles, again our point of reference is B, which is a common joint. Now for this one is the opposite of the first method. So the first method, you said that to identify A, you identify it by a common joint. So a section which is so close to a common joint is A, and then the remaining one is B. And for this one, the second alternative, or the alternative one, now you are moving from this side, going to a common joint while calculating the centroid. So be keen and know what you are doing while calculating your centroid. So after calculating these areas and centroid, now we will go to a 2 x bar 2. As you can see, this figure is a parabola. We said earlier that a UDL will bend in a parabolic shape like this one, and the area for that one is 2 over 3 times base. Base is the length, which is 5, times h. H is the maximum bending moment for that span, so it's 68.75 times the centroid. The centroid for this one is L over 2, so it will be 5 over 2. So this one will give you 572.92. Now, after having calculated the value for A1 x bar 1, A2 x bar 2, we can now insert the known values in our formula so that we can get our unknown. So let me wrap this one to create a space. So I can wrap this one. This is our formula. Let's now begin inserting the known values in the formula. So the MA is unknown. L1 is 2 plus 3, that is 5. So it will be 5 over I1 is I. The coefficient to I is 1. MA plus 2 MB. So L1 again is 5. I1 is 1 plus L2. L2 is this distance. So that is 5 over I2. I2 is 2I. So the coefficient there is 2 plus MCL2. So ML2 I2 will be 5 over 2 MC should equal to negative 6 into bracket A1 x bar 1 is 112 over L1 I1, that is 5 times 1 plus A2 x bar 2, that one was 572.92 over L2 I2 5 times 2, like that. Now you can simplify our equation. So we have 5. Okay, after reaching there, you can easily eliminate some figures from this equation by saying that, but moment at A is equal to moment at C and is equal to 0, because it has a pinned support. So this one is simply supported. Also, this one is simply supported. So those one, the moment is always equal to 0. So here will be 0. Okay. Now we come to this one. 5 over 1 plus 5 over 2. 5 over 1 plus 5 over 2. That one will give you, so this one will be 7.5 times 2, that is 15. 15 MB. MC again is equal to 0, because if you multiply 5 over 2 times 0, it will give you 0. The same to this one. So should give you minus 6 into bracket. Give me get the figure for this one. Negative 79.692, like that. So that is it. So after doing so, this one will be 15 MB should equal to negative 478.152. So you divide both sides by 15 by 15. So MB is equal to negative 31.88 kilonewton. So that is all about bending moment. So the question part A, it says that analyze the beam and hence plot bending moment diagram indicating values at critical points. And then number 2, calculate the reaction and hence draw shear force diagram indicating critical values. So after having done so, we now go to our reactions. Now we'll find reaction at A, reaction at B, and then reaction at C. And to do so, we split this beam. It's a continuous beam, so we'll split the beam into a simply supported beam. So this is how we will split. So we start from here. We have joint A. It's a single joint. And then you go to B. B, it has a joint which is in between two lengths. So you will split that one like that. And then joint C is a single joint bordering one length. So this one is splitted into RB1 and RB2 because it is bordering the two lengths L1 and L2. And this one will remain RC. Again, this one will remain RA. So we have this 16 kilonewton, and then we have this one as 22 kilonewton per meter UDL. So we have 2 meters, 3 meters, and then 5 meters. This is A, B, C. So at C, we have moment. At C, we have moment, which we have just calculated as 31.88. At 1.88. At C, we also have moment, but it is 0. Again, at A, we have moment, 0. So let's begin calculating the reaction. So here, we have splitted this continuous beam into a simple supported beam. So a simply supported beam is a beam which has only 2 supports. You can see this is 2 supports, this is 2 supports. So for you to analyze such a beam, you'll use the 3 equation of static equilibrium. So we go back again to the 3 equation of static equilibrium, which will help us to find reactions at A, at RB1, RB2, and at RC. So we start with this one. Let's begin by summing moment about a point. So summation of moment at RA is equal to 0. So when you sum moment at RA, automatically you'll be calculating reaction at RB1. So in which reaction is RB1 moving in reference to RA? So it is 2 plus 3, that is the distance, times this force, which is a reaction. In which direction? Anticlockwise, so minus 5 RB1. So something to note, moment is distance, perpendicular distance times a force. So as you can see, RB1 is our force, and 2 plus 3 is our perpendicular distance from RA. So minus RB1. It is moving in anti-clockwise direction. And then we come to a moment which is 31.88. So this one is already a moment. There is no need to multiply it by the distance. So we only multiply the distance when we are dealing with forces. So this one is already a moment. So you just take the way it is, and then you consider its direction. So the direction for this one is moving in clockwise direction. So it will be plus that 1.88. Again, after doing so, we come again to 16 kilonewton in each direction clockwise. So plus 16 times 2. So it should be equal to 0. So minus 5 RB1 plus, you can get the total, or you can punch your calculator to get the answer for this one. So that one will be 63.88. 63.88 will give you 0. So which imply RB1 is equal to 12.78. That is RB1. So what I have just done here is to get this one cross to the other side. It changes sign from negative to positive, and then you divide both sides by 5. You'll get 12.78. So again, let's get RA. So we know that summation of upward forces is equal to summation of downward forces. So the upward forces is RA plus RB1, and the downward forces is 16. So don't include the 31.88, which is a moment. Only deal with forces when applying this static equation of equilibrium. So RA, this one is plus RB1. So RA, we don't know RA, we only know RB. So RA is equal to 16 minus 12.78, which is equal to 3.22 kilonewton. So that is RA. Again, after dealing with this section, we go to this one. So let's some moment about RB2. So summation of moment at RB2 is equal to 0. So automatically what we are looking is RC. In which direction is RC moving in reference to point to where we have some moment from? So that is anti-clockwise direction. So that is minus 5 RC. Then we come to this moment that 1.88, in which direction is moving in reference to RB2, is moving anti-clockwise. So that one will be minus that 1.88, like that. And then we come to a UDL, which is 22 kilonewton per meter. It starts from here and it ends here. So in which direction? Clockwise. So plus 5 times, no, 22 times 5 times 5 over 2 should give you 0. 22 times 5 you will change to a UDL, and then times 5 over 2 at the center of the beam. That is where a moment for UDL is. So this one will give you minus 5 RC. Also punch your calculator. Plus 243.12 plus 243.12 should give you 0. which imply RC is equal to 48.62 kilo Newton. So after doing so, again we'll have to calculate the reaction at RB2. So we say that summation of upward forces is equal to summation of downward forces. So upward forces is RB2 plus RC. So it will be RB2 plus RC, which is 48.62. This one should give you 22 times 5, because the downward forces is a UDL. So 22.5. So this one imply RB is equal to, you can continue doing the operation here. It's just mathematically, and then you will obtain RB. RB2 which imply RB2 equal to 61.38 kilonewton, 61.38 kilonewton. So after doing so, you can now draw your shear force diagram. So let me wrap this one to create space. So we know that RA is equal to 3.22. RB is equal to RB1 plus RB2. So this one will be 12.78 plus 61.38. So this one should give you 74.16 kilonewton. And then RC is equal to 48.62 kilonewton. Having done so, now we can draw our shear force diagram. So let me use a different pen to draw a shear force diagram. So let's draw the baseline. So that is the baseline. So RA is 3.22. You can approximate here from the baseline to 3.22. So somewhere like that. So this is 3.22. So 3.22, it will be constant up to the next react force, which is 16. So you will take 3.22 minus 16. So it will give you negative 12.78. So you approximate here 12.78, like that. Again, after there, it will be constant up to reaction at B. So take negative 12.78, add reaction at B. So plus 74.16, that is 61.38. So somewhere like there. 61.38. Now 61.38 minus this UDL, because it is acting downward on the beam, so it is 22 times 5. That is 110. So minus 110, 48.62. So that is 48.62. So 48.62 is somewhere like there. So you draw a diagonal line. That is 48.62, negative 48.62, and then plus reaction at C, you go back to 0. So this one will be plus, minus, plus, minus. Like that. Now we have come up with our reaction and draw the shear force diagram indicating critical values. So these are the critical values, like that. Now the next thing to do is to plot the bending moment diagram. So this is our point where our shear force is changing from positive to negative. So that point will give us our maximum bending moment. So that maximum bending moment will be used to design such a beam. So for you to tackle question A, there is two methods to draw the bending moment diagram. So as you have seen, we have calculated and find bending moment at C is that negative 38 point, negative 38 point, no, negative 31.88. So there is two versions of drawing the bending moment diagram. So there is this one. After calculating that value for bending moment at B, we'll approximate along this line where that 1.88 is. So let's say it's above 19.2, but lower than 38.75. So this one, let's say this one is 38, 31.88. So you'll join. Here is 0. Here bending moment was 0. So you will join here to this line, and then you join here to, like that. Yes, like that. So after having done so, this one will be negative. That one will be negative, and this one positive. Now you have combined the two moments. The first moment we calculated was the moment for free span. And then we have calculated another moment, which is 31.88. So it's 31.88, but it is negative. So that is the first method to draw a bending moment diagram. We have another method which is more professional for people who are practicing structural engineering. The second method is this one. You draw your baseline and you say that BMD, remember this one was shear force diagram. And after doing so, we'll now start calculating values at respective points, like point A, point D, point B, point C. And for you to begin calculating the values, first, find this distance. Call it X. So this one will be 5 minus X. Why? Because at this point, we will have our maximum bending moment, because the shear force is changing sign from positive to negative. And this maximum bending moment at this line will be used to calculate or to design this beam. So if we assume this one is X, then the remaining one will be 5 minus X, because from here to there is 5. So using a similar triangle method, we'll say that X over this distance over from here to here, 61.38, should be equal to this distance 5 minus X over from here to here, 48.62. So which imply, so this one will be 48.62 times X. So it will be 48.62 X should give you 61.38 times 5. 61.38 times 5. 306.9. So 306.9 minus 61.38x. This one cross to the other side, 48.62x plus 61.38x should give you 306.9. Then plus 48. So 110x should give you 306.9, which imply x is equal to 2.79. So x is 2.79. So the remaining one will be 2.21. So 2.21. Now you can be comfortably say that our point y is 2.79 from B and 2.21 meters from C. Now you can now start calculating our bending moment. So bending moment at A is equal to 0. So bending moment at D, it will be the area of this one. So it will be 3.22 times 2. So this one will be 6.44 kilonewton meter. So bending moment at B will be B bending moment at D, bending moment at D, which is 6.44 minus bending moment for this shape, which is a rectangle and it is a negative. So minus 12.78 times 3. So this one will give you negative 31.9. As you can see, this was our BMD, our bending moment at here from our first equation. So again, you have proved and found it is the same value we obtained in our first case. Then bending moment at Y, which will be our maximum bending moment. So it will be bending moment at B, which is negative 31.9, negative 31.9, negative 31.9 plus the area for this one. So that one will be a half or a 0.5 times 61.38 times 2.79. So this one will be 53.73 kilonewton meter. So that is our maximum bending moment, and during the design, this is the value that will be used to design such a beam. And bending moment at C is equal to 0 because it is a pin support. So now you can draw our bending moment diagram. So here is 0. At D you have 6.44. So let's say 6.44 like there. And then at B you have, so this one down, and then that 1.9 is negative. So it will be that one somewhere like there. That 1.9. And then the last one is 53.73. So 53.73. So you can join. This one will be a diagonal again. This one will be a curve. Again, this one will be a curve. So here is plus, minus, plus. So as you can see, as you can compare this one and this one. So this one is more professional. It is very easy to have a look and know how the BMD is behaving than this one. So I prefer you go for this one rather than this one. So that one, it marks the end of that question. It was 20 marks. So Having done so, we have scored our 20 marks.